This is May 2024 paper. Question number one is bromate ions react with bromide ions in aqueous acid. The rate equation for the reaction is shown. Which continuous monitoring method could be used to obtain kinetics data for this reaction? We have to see like what what are the reactants and what are the products in this reaction. As you can see, we have bromine in this reaction, isn't it? And bromine is colored. And if we want to measure the rate of reaction, so we can check the color of the bromine. Okay, since we have a colored species in this reaction, that's why. So I can say it's going to be calorimetry. Basically, we have two processes, calorimetry and calorimetry. There is a difference between calorimetry and a calorimetry. In calorimetry, we measure color. In calorimeter, we measure heat. So that's why it's going to be A. So that's why it's going to be A, right? What are the units of the rate constant for this reaction? The units for the rate constant for this reaction. So it's gonna be, let me calculate it. K would be equal to, K would be equal to over, rate over, I'm going to sum it, right? It's power 1, it's power 1, it's power 2, it's going to be total power 4, isn't it? So the concentration raised to the power 4. Now I'm going to simplify this since I know that the unit for the rate is mole per dm cube per second. And the unit for concentration is mole per decimeter cube raised to the power 4. Going to be mole per dm cube per second. I'm going to apply the power. It's going to be mole 4 dm minus 3 fours at 12. Then I'm going to simplify this. It's gonna be mole per d. No, 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 no. It's going to be 1 minus 4 and dm minus 3 plus 12. Second remains the same. It's going to be mole minus 3 dm plus 9 and per second. So it's mean that it's going to be d, isn't it? Right? So in this way, we can find out the unit. And okay, then we have the concentrations of all the reactants are halved. The concentrations of all the reactants are halved. By what factor does the rate of this reaction, uh, by what factor, by what factor does the rate of reaction change? So, you know, in this, all the reactants are halved. Like this is halved, this is halved, and this is halved. So the power is 2. So it's going to be 1 by 4 into 1 by 2 into 1 by 2. It's going to be 4 into 2 is 8. 8 into 2 is 16. So it's 1 by 16. It's going to be D. The first four steps in the reaction mechanism are shown. Which is the rate determining step? Which is the rate determining step? And the rate determining step is the one, the rate determining step is the one which is supposed to be the slow step, which is supposed to be the slow step. And it is generally observed that when the bond is being formed, when the bond is being formed is a faster step. When the bond is being formed is a faster step. And when the bond is being broken down, it's a slower step. And when we have a slower step, it's gonna be the rate determining step. So out of these four steps, we have to identify in which step the bond is being broken down so that I can say it's going to be the slower step, and that's gonna be the rate determining step, right? So I can say in the first one, the bond is being made, it's a faster step. It's wrong. In this way, the bond is being formed. It's a faster step. It can never be the rate determining step. And then if we can see, it's BrO3 and it's Br2O2, right? So means that the bond is going to be broken down. So that's why step 3 is the rate determining step. That's why. Okay. So okay, then you can see some data on lattice energies are shown. Which compound has the greatest degree of covalency with its ionic bond? Covalency with its ionic bond. So, um, basically, lattice energy will be telling us the strength of an ionic compound. If the lattice energy is more exothermic, like it's going to be more negative, so the compound would be more stronger. I'm talking about ionic compound because the term lattice energy is specific to an ionic bonding, ionic compound, right? So what they are saying, which compound has the greatest degree of covalency with its ionic bond? Since you can see that um, uh, A says NaI. So its experimental lattice energy is minus 705 and theoretical lattice energy is minus 687, So this is going to be incorrect, okay? Or if I can see AGBR, if I can see AGBR, AGBR. So if you can see this one, uh, minus 891 and minus 816. Like the difference is, can you subtract it and tell me what's the difference between them? Minus 705 and plus 687. Can you tell me the difference? Yes.
Minus 18, negative 18.
Sorry, minus 18.
Negative 18,
Okay. And what's the difference in these two values?
minus 75.
Minus 74.
75.
75. Okay. And what about this one? I think it's gonna be 31, isn't it?
Negative 40. 40.
Negative 40. Okay. Yeah, 40. Sorry. And what about this one? It's going to be um
15. Negative 15.
so the bigger difference is B. So yes, AGBR is correct. Greatest degree of covalency within its ionic bond. So the difference is supposed to be higher. An enthalpy cycle for lead 2 nitrate is shown. All values are in kilojoules per mole. Yes.
Sir, can you go up? I just want to take a screenshot.
Okay.
Thank you.
Or which of these statement is true? All the values are in kilojoules per mole. This cycle is not to scale. Okay. The enthalpy change of formation of lead 2 nitrate is minus 2151 kilojoules per mole. So minus 2151. They are saying enthalpy change of formation, right? Enthalpy change of formation. Uh, this is not formation. This is lattice energy, isn't it? It's not formation. It's a lattice energy. They are. This is incorrect, right? This is incorrect. The enthalpy change of solution of lead 2 nitrate is exothermic. So lead 2 nitrate is exothermic. So if we can see, uh, when lead 2 nitrate is going to be dissolved in water, so they are saying the solution is going to be exothermic. Uh, Solution may be both, it may be exothermic and it may be endothermic. So it's changing from, you can see, solid to aqueous. You know, you can see this one. First of all, it's going to be solid, then the aqueous is added, and then it's converting into aqueous. It's called hydration. Solid to aqueous is solution, but this is positive value. So why they are saying it's going to be exothermic? No, it's incorrect. It's endo. So that's why statement B is also incorrect. Or C says the enthalpy change of hydration of a lead ion is more exothermic than that of a nitrate ion. Since we know that lead 2 plus is a cation. Lead 2 plus is a cation as compared to the anion. Nitrate ion is an anion. The size of cation is smaller than anion. When the size of cation is smaller, so it's mean that when the water will be attracting the positive ion, due to the greater attraction, more energy is released. So that's why hydration for lead ion is more exothermic. That's why C is correct. Okay. And they are saying the entropy change of the surrounding for dissolving lead 2 nitrate is positive. Okay, entropy change of the surrounding dissolving lead nitrate. Dissolving lead nitrate is going to be endothermic overall. So endothermic means the energy is being absorbed. So the energy of the surrounding decreases. So the entropy should decrease, but they are saying entropy is positive. So it's wrong. That's why C is correct, right? Using the enthalpy cycle, it can be calculated that the enthalpy change of hydration of a nitrate ion in kilojoules per mole is this one. Hydration. You know what is hydration? You know what is hydration? Hydration is when something changes from gas to aqueous. Remember, hydration means when something changes from gas to aqueous. Okay, so we can calculate the hydration they are saying. So we can calculate it. So what would be the value? What do you think? I have to calculate from gas to aqueous. I have to calculate from gas to aqueous. So what do you think? What is supposed to be the answer from this cycle? We have to use this cycle only.
Sir, can I see the options for the answer?
Minus 3598, and then we have minus 1799, 628, and then minus 314. Hmm?
Oh, I'm still doing that.
You can see the values as well. And they are only asking about the nitrate ion. Remember, they are only asking about the nitrate ion, by the way. Basically, if I talk about the hydration of nitrate. So as I told you, hydration is from gas to aqueous. As I told you, hydration is from gas to aqueous. So this is going to be hydration. Remember, you need to know the state symbols. That will help you a lot in identifying the process, right? In identifying the process, they will help you a lot. What is solution? What is hydration? What is lattice energy? Like in ionization, what we do, in atomization, what we do, information, what we do. So like these kind of things, it can give you a like shorter way to do the question. So I just knew the state symbols. It's gonna be gas and it's going to be aqueous. So I know that it's going to be hydration. So 2 nitrate. 2 nitrate. First of all, I have to find out this value. So how can I find out this value? Can you tell me what I would be getting if I'm going to subtract it? Yes.
Minus 3,636.
Oh my God, I'm subtracting it.
No. Minus 666.
Minus, like you're saying that
666.
minus 2,151,1,485. It's gonna be how much?
Minus 666. Yeah.
And what if I'm going to put this number minus triple six plus 38?
Minus 628.
So this is going to be hydration for the nitrate. And of course, I have two nitrates. I have two nitrates. Okay. And the mole ratio between this one and this one is 2:1. So I have to divide it by 2. So what's the answer? If I'm going to divide it,
Minus 314
so that's the
CD.
answer. Yeah. Ammonia is produced from nitrogen and hydrogen in the presence of a solid catalyst. In an equilibrium reaction, 10 moles of nitrogen is heated with 10 moles or 30 moles of hydrogen in a sealed container at equilibrium. At 8 moles of ammonia is present. What is the total amount of gas in mole in the equilibrium mixture? So, then I'm giving you only 1 minute. Then I'm going to solve it. First, I told you initial amount reacted, amount produced, equilibrium amount. So you can do that method and you would be getting the equilibrium amount.
Sir, I got C.
Uh, okay, okay. So means that I have, let's say N2 plus 3H2 and 2NH3. 10 moles of nitrogen, 30 moles of hydrogen. It's going to be zero. How much reacted? How much produced? 8 moles of ammonia is given. Okay, so I can find out the value for x. 2x is equal to 8.0, x is equal to 4.0. It's going to be 10 minus 4, that is going to be 6. It's going to be 30 minus 3 into 4. 30 minus 12 is going to be um 30 minus 12 is, oh my god, 18, right? No?
Yeah,
Yeah, 18. So 18 plus
18,
6 plus 8.
32.
32 is your answer. Sorry, C is your answer, right? It's not D, it's C.
So it says C.
Okay, good. Now see this one. This is your equation, and you have to find out the Kp. So what should be the Kp? You know, Kc and Kp, they
Sir,
are
can
the same thing. Product upon reactant.
I see the equation?
Sir, is it C?
Uh,
Yeah, I
good,
got
good.
C as well.
Yeah, C is correct because the formula is product upon reactant. Yes, good. The coefficient becomes power. Yeah, okay. So see this.
Decreasing the temperature because only temperature is affected, I think.
Increases the value for Kp. So increases the value for Kp means that Kp is a constant and Kp only changes with the change in temperature. Remember, Kp only changes with the change in temperature. So that's why A is going to be correct. See this one? For all chemical reactions, the equilibrium constant K is related to the total entropy change delta S total by the expression shown delta S total is R ln K. Delta S total for a reaction is negative. Which statement is true? So they are saying the value of K is, I have to have the delta S negative. So how can I get the negative delta S when the value of K is less than 1, when the value of K is greater than 1, when the value of K is negative, when the position of equilibrium lies to the right? So remember, if I would be having the value of K that is less than 1, okay, in that case, because we know the R, that is going to be the constant. So if you have the value for K that is less than 1, so when you will be solving it, so you will be getting the negative entropy change. You will be getting the negative entropy change. So means that that is going to be A. See this one? And we can also say about this question, like delta S total is directly proportional to ln K, is directly proportional to ln K, right? So if this is going to be negative, if this is going to be negative, so remember L and K is negative because they are directly proportional. Okay. So K is, should be less than 1. That's why. That's the also logic that you can apply. A buffer solution contains CH3COOH and CH3COONA in the ratio of 1:4. What is the pH of this buffer solution? We know the Henderson-Hasselbalch equation that says that pH is equal to pKa plus log into the concentration of salt divided by the concentration of acid. So pKa is the negative log of Ka, that is 1.7 exponent minus 5 plus log, and then I can put 4 upon 1. Okay, because 1 is this and 4 is this. So then we can solve it. So what's the answer that we are getting? Hmm?
5.4.
So D is correct, right? Okay, good.
Yes.
Or. Okay. The accumulation of carbon dioxide during exercise reduces the pH in cells in blood. Which of these reaction is most important in buffering the decrease in pH that occurs? Blood is also a buffer solution. Blood is also a buffer solution. And what's that system? It's a mixture of carbonate and bicarbonate. It's a mixture of carbonate and bicarbonate. So means that it's going to be B. When bicarbonate reacts with H plus, it produces H2CO3. Which of these reactions is most important in buffering the decrease in pH that occurs? So if you remember when we were discussing um, how the buffer solution works. So when we were adding acid and when we were adding base, so I used to tell you that when you are adding small amount of acid or bases, so the buffer solution will tend to oppose the change. It's not going to, it's not letting you to change the pH of that solution. So the buffer solution will change its position. Like sometime it goes forward, sometimes it goes backward to to resist the change in pH. So that's what we do in a buffer solution, right? So that's why B is correct. Okay, how many chiral centers are there? One, two, three, four, five, six. No, 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 no. Because double bond is not a chiral center at all. One, two, three, four, five, six. So I have six chiral centers. We are not supposed to look at the double bonded carbon, right? Can never be a chiral center because what's the chiral center? It's sp3 carbon, like I mean to say single bonded carbon having four different groups attached. So, okay. The rate equation for the hydrolysis of a halogenoalkane Rx is in aqueous alkali is shown. Which of these statements is true? And this equation suggests that it's a first order reaction. The mechanism involves a carbocation intermediate. And we know that. And we know that it's SN1 reaction, isn't it? Because that's why the order is first. For SN2, the order is 2. And SN1 reaction occur in two steps, if you remember. And in two steps, there is a carbocation intermediate form. Carbocation intermediate is formed, right? So yes, A for apple is correct. So we need to know this. Yeah, we need to know this. What happens in SN1 reaction? What happens in SN2 reaction? So we must know these things. Propanol reacts with HCN in the presence of KCN. Which of these statement is incorrect? Cyanide acts as a nucleophile in this reaction. So propanol is this one, right? So propanol is this one, or in the presence of KCN, uh, which statement is incorrect? This is correct, right? Cyanide is having a negative charge. Cyanide is having a negative charge, and it's going to be propanol when the cyanide will react with this one. So, you know what will be the product? You know what will be the product? It's going to be this one. This would be the product, right? So a racemic mixture is formed. No, this statement is incorrect. So that's the answer. You know why this is not a racemic mixture? Because there is no chiral center. You know, there is no chiral center. That's why this is not a racemic. Racemic mixture is the one in which we can see the chiral center. Racemic mixture is the one in which we can see the chiral center. So this statement is incorrect. Now, which statements are correct? CH3, CH2, COCl. It's carbonyl chloride
Sir,
reacts with, yes.
if there's no chiral center, will it also not be optically active?
Yeah, it would be optically inactive if there is no chiral center.
Okay, so if there's a racemic mixture, it will be optically
Racemic
active,
mixture,
right?
racemic mixture means that 50-50% we have in enantiomers. 50-50%. Okay. It's called racemic mixture. And in enantiomer means that the chiral center exists. But in this, you can see two CH3s are same. So there is no chiral center. And if there is no chiral center, so no racemic mixture. Yes, question number 11 says CH3, CH2, COCl reacts with CH3, NH2 to form CH3, CH2, CO, NHCH3. What do you think? What's going to be correct? CH3, CH2, COCl reacts with what? You can react and then you can see, is that forming? Yes or no? So you will come to know what's going on.
Sir, is it B?
Uh, B means that when CH3 C double bond OCl will react with CH3 NH2, so it would be forming. Yes, it's true. One is correct. Let me check B as well. CH3. This is also correct. Okay. Let me check 3 as well. No, it's a tertiary, no reaction. It's a tertiary. It's a tertiary, no reaction because it's going to be positive, right? So 1 and 2 is correct. Good. It's a tertiary, that's why. An ester is hydrolyzed in excess dilute hydrochloric acid to form ethanol and propane dioic acid. What is the skeletal formula of this ester? So ethanol is going to be this is ethanol, right? And propane dioic acid is going to be 1, 2, and 3. So I am supposed to have two alcohols, right? It's a dioic acid. So when they will be reacting, when I'm going to share my screen. When they will be reacting, so they will be forming, um, they will be forming A, isn't it? Because, because water is removed and water is removed. So they can attach with each other. And you can see this ester. Simple. A is correct, right? Which compound has the most peaks in its carbon 13 NMR spectrum? So it's going to have three peaks. It's going to have 1, 2, 3, 4 peaks. It's going to have two peaks, one and one, because it's the similar structure, right? Oh no, it's going to have three peaks. You know why? One, one, two, two, and three, right? Due to the similar structure. And it's going to have one, one, two, three, four, five, six. It's also a symmetrical structure. It's also a symmetrical structure. One, one, two, two, three, three. One, one, two, two, three, three. It has three peaks. So yes, it's going to be B. It has more peaks. 14. The high resolution and MR spectrum of an aster is shown. What is the skeletal formula of this aster? Use the data booklet to as a source of information. Let me first see what's going on in this one. So first of all, I can see I have three environments. First of all, I can see I have three environments. Okay, in which one I can have triplet, then singlet, then doublet. Okay, no, then it's a quartet, right? It's a quartet having two hydrogen atoms. Singlet with nine hydrogen atoms. So, whenever you can see this one, so it's mean that it's going to be somehow like CH3, then CH3, then CH3, and there is no neighboring hydrogen. So that's why I'm getting the singlet. So I can have an idea after looking at this structure, it's going to be rather C and rather D, isn't it? Isn't it? Makes sense. A and B is completely incorrect. Or then I can count the total number of environments. I think environments would be the same because this is a symmetrical structure. Now we have to see the value from the data booklet, you know, and also the ratio. The ratio is very important. They are saying that the ratio is 9 is to 3 is to 2, isn't it? They are saying 9 is to 3 is to 2. And also, I can say that um, I can say that over there should be a peak of HC, C double bond O, right? You can see this one, but there is no. So it's mean that it's going to be D. Because in D I have C and then C double bond O, and C has different branches. So it confirms that it's going to be D. And now you can count the ratio as well. Three hydrogens, three hydrogens, it's 9. And then I have two hydrogen atoms. So it's going to be 9 is to 2, 9 is to 2, 9 is to 3 is to 2, right? 9 is to 3 is to 2. You can see the ratio. So we have three different proton environments in this. We have three different proton environments. So 9 is to 3 is to 2 is the total ratio. If you can see like option D, right? Yes.
So I still don't understand the ratio part.
Basically, ratio means that they have told you it's going to be nine hydrogens having the same environments. That's why I'm getting singlet. And in this, I can have three hydrogen atoms. Okay, it's going to give you triplet. You know why are you getting triplet? Let's suppose if I have CH3, let's suppose if I have CH3, so how many neighboring hydrogens you have? Two. So we generally apply the rule n plus 1 rule. So neighboring hydrogens are 2 and then 2 plus 1. It's going to be 3. That's why I'm getting triplet. Okay. And if you can see this one, if you can see this one, how many neighboring hydrogens I have? 3. So it's going to be n plus 1 rule. So 3 plus 1 would be giving you 4. So you can get the quartet. And we are getting the quartet. You can see quartet. Okay. Are you getting this? Because in a quartet, I have two hydrogen atoms. And in a triplet, I have three hydrogen atoms. You can see.
Okay, sir, thank you.
This is called proton to proton ratio. And then the graph would be telling you whether they have the neighboring hydrogens or not. Like this is going to represent that there is no neighboring hydrogen. That's why all the nine hydrogens have the same chemical environments. Right?